In today's session, I shall demonstrate a very powerful debugging technique which can be used to locate the faulting function out of a mere faulting address that we have without the use of a debugger or any other tools, except for two very small, simple utilities which are part of any Linux distribution. Assume, for example, that we have an application named test, which has crashed in the field. Because of various circumstances, all that you know is the exact address where the fault happened, but you don't know anything else about the environment or the application. What I'm about to show you is how to take this information that you have, the fault address, and to gain some very good guess about which function that fault occurred in. Let us start. First line of business is to understand whether the fault happened in a function, which is part of the application code itself, or rather, in the code of a dynamically loaded library, which is loaded by application. In order to do so, we shall apply the simple tool LDD. We'll run it and provide it with the name of the application as its parameter. What LDD does is provide us with a list of all the dynamically loaded libraries which the application uses, and, most importantly, also the load address of each of these libraries in the specific run that we've done now. These load addresses are semi-fixed. They will be fixed as long as we do not change either the application code or any of the dynamically loaded libraries. What we'll do is we'll compare the fault address that we have with the load address of each of these dynamically loaded libraries. If the fault address is near one of the dynamically loaded libraries' load address, we can safely assume that the function that failed is within one of these libraries. If, however, the fault address is not near any of these addresses, we will safely assume that the fault occurred in a function which is part of the application itself. Let us now assume that the fault occurred in the application itself. That is, our fault address does not lie near any of the load address of these functions. What we shall do is use a small utility called nm in order to view all the symbolic information of the application. We shall apply the -a parameter to nm and pipe the result into the less utility in order to be able to view the output easily. Here is the output of nm for our test application. As you can see, it comprises of address, a type of symbol, and the name of the symbol. Many of these symbols are internal symbols used by the mechanics that load the application itself. However, these which are marked with a capital T actually mark the name of functions which are defined inside the application itself. What we need to do is to take the fault address that we have and search for it in the addresses for the symbols. If we find, for example, an address which is identical or even close to one of the addresses which are marked by a capital T, we know that the faulting function was the function whose name is displayed next to that address. Note that the faulting address need not be identical to the exact address of the symbol. It might be slightly higher than it. The reason is that it is very possible that the fault occur not at the beginning of the function, but someplace after the beginning. However, what happens if the fault address is near one of the load address of one of these dynamically loaded libraries? In that case, we shall apply nm again, however, in a slightly different manner. First of all, what we'll have to do is take our fault address and subtract from it the load address of that library in which we suspect that the function is defined. We know which library it is because the fault address would be near, slightly higher than that function. Having subtracted the fault address from the load address, we now have an offset into the dynamically loaded libraries, which we can use to find a function, just as we have done previously with the application itself. We will run mn again, this time supplying it with the D, capital D parameter, in order to notify it that we are interested in dynamic symbols, which are defined inside dynamic loaded libraries, and we'll supply the path or the name of one of the libraries which we wish to inspect. We know which library it is because the output of LDD shows it. Once again, I shall pipe the output to less in order to be able to easily view it. Here too, we get a list of all the symbols which are defined inside these dynamically loaded libraries. And once again, all the symbols which are defined or marked with a capital T are actually the name of functions defined in the dynamically loaded libraries. However, unlike what we've seen with the application itself, the address near each of these symbols is not an absolute address. It is rather an offset from the beginning of the dynamically loaded library code. Therefore, we shall compare the offset which we have computed before between the fault address and the link address of the dynamically loaded library with the offset displayed here. And for example, if we found that that offset is very much close to something which is displayed near one of the capital T marked symbols, we can safely assume that our faulting function is one which is named or described by the name of the symbol which is next to the line. As before, it is important to note that it is very possible that we will not see an exact offset as marked here, but rather something close to it, probably a little higher. Again, the reason may be because the fault occurred not at the beginning of the function, but rather some code after it. What we've seen today is that using only the fault address of a failing application and the two utilities, LDD and NM, we are able to locate the name of the function in which the fault occurred. I hope that was useful to you. Thank you, and bye-bye.